Okay, so for this experiment, we're looking at efficiency. So just remembering that we calculate efficiency by using, when we've got an energy transfer, the useful energy divided by my input energy multiplied by 100 to put it in terms of a percentage. Okay, so when we're looking at this first experiment, we've got a bouncing ball. So we're dropping the ball from a height, remembering that when we're dropping the ball, we're just releasing it. Okay, I'm not throwing it, so I'm only going to be giving it its initial gravitational potential energy. Okay, so we're just dropping it, so it's going to have its full GPE at the top. So we're going to start with gravitational potential energy. That is going to change down, and as it goes down, it accelerates and it turns into kinetic energy. Okay, so we have GPE going into kinetic energy. Okay, and then it's going to then rebound and bounce back up, so it goes back into GPE. Now, if this was a perfect system and it was completely efficient, we would expect it to bounce back to exactly the same height, because all my GPE would go to all my KE, would go to all my GPE. But that is not the case. We actually have some wasted energy here. Okay, we have a bit of thermal, okay, being given off. We also have some sound as it hits the ground. So that means my kinetic energy here is going to be smaller than my gravitational potential energy, which means that my gravitational potential energy after, okay, is also going to be smaller. Okay, so in this case, we're looking at that useful divided by my input. So in this case, that's going to be the GPE after divided by the GPE before. So in this case, our independent variable would be the height, so our GPE before, and our dependent variable is going to be efficiency. Is it more efficient at great, so as I said, why some wasted, we know some was wasted from sound and heat. And then I've got, is it more efficient at greater heights or smaller heights? So this is kind of looking at our hypothesis here. So if we drop it from higher heights, do you think it's going to be more efficient or less efficient? What I would think about here is I'd think about, well, what's it causing waste energy? Okay, waste energy is caused by that heat loss, okay, and a little bit by that sound. Well, the higher it travels up, the more air resistance it's going to encounter. Okay, so there's going to be more thermal energy. So what does that make you think about the efficiency? That's what I would be using there. The other thing as well is just to remember that GPE, okay, is equal to mass times gravity times height. So if we're going to be doing the equation there, GPE before divided by GPE after, m times g, so that's our initial, and this is our height of our rebound. I can actually cancel my m and my g, so I don't need to have those considered in the experiment. I can just do the efficiency calculation like that. Or you could go through and calculate GP, but you just don't have to do that step. The other experiment that you guys could do at home was the one where we were going to be increasing the height of a ramp. Okay, now some of you are talking about therefore that it increases the angle, and that is true, it does increase the angle, but we're going to be trying to talk about the energy, so we're going to try and talk about the height. So again, the independent variable is going to be the height of the ramp. Okay, the dependent variable for all of them is still going to be efficiency. So in this case, what's going on? Well, it's got at this point its GPE, and its GPE is rolling down the ramp, it's decreasing its GPE and turning into kinetic energy. So we have GPE going to kinetic energy. So in this case, I've got my mgh going into my half mv squared. All right, now if this was fully efficient, my KE down here should equal my GPE up here, but that isn't always the case. Okay, we actually have, again, we have some thermal coming from the friction and the air resistance. We also maybe have some sound as it rolls down as well. So it isn't going to be 100% efficient. So we have to use that efficiency equation of the useful divided by the wasted. So we're going to be doing KE divided by GPE. Now just remember, to calculate KE, we have to do a half of the mass times the velocity squared. Now, for this one, we can't actually measure the final velocity at home. It's a little bit difficult, so we're going to kind of cheat a little bit with this and actually do average velocity, which isn't the best scientific method, but it is something that we are able to do for distance learning. So speed is equal to distance divided by time. So we're going to do the distance as in the length of the ramp, and we're going to time how long it takes to go down. So you're going to have to calculate the velocity to then be able to work out your kinetic energy, to then be able to do your efficiency, of your efficiency is going to be equal to KE divided by GPE. Okay, again, having a little think, when does it travel faster? Does it travel faster at higher heights or smaller heights? Is that going to create it to have more wasted energy or less wasted energy? How does that affect the efficiency? Okay, so thinking about that should help you come up with your hypothesis for if you were doing the ramp one. So each time you're doing it, you want to be talking about the energies, you want to be talking about what efficiency is, and you want to think, how am I going to affect the efficiency? Okay, so thinking about the forces that are causing it to slow down, that's causing it to have waste energy. Be really careful, as in the lesson, a few of you kept telling me that it was wasted forces. It's wasted energy, but it's caused from the forces. Okay, so air resistance causes wasted energy of things like heat loss, for example. So hopefully that helps with a little bit of a summary there.